mathematical step, which I'm sure you will have guessed, consists in doing exactly the same machinery, the same stuff, but now with the curl. Okay, again, I'll just give you all these equations. You have them on the site anyway. It's a great exercise for you to do it, to try to do it from scratch. But once again, this is a calculation that you do once, well, and then you've done it. Okay, so let's walk through it in a few minutes. What am I doing? Same thing, but now with the curl operator. I start again from my most generic form of Biot-Savart, the one where I volume integrate over the volume charge density. Left-hand side, curl of B is equal to the integral of the curl of this very same product of things I had before. And again, I use exactly the same tricks. I again replace this r over r cubed by minus the gradient of 1 over r. So this thing simplifies to now the curl of a cross product. Okay? Instead of a divergence of a cross product, we now have a curl of a cross product. Absolutely the same story. Once again, a differential operator applied on a product of vector field functions like that should operate linearly, namely give you a sum of lots of different terms. There are identities to save you in this, which are in the lecture notes and in the books. The one that you need is for the curl of a cross product, which is just given here for generic vector fields A and B. Okay, again, don't know this by heart. It's tabulated. You can just use it. Okay, so again, doing absolutely exactly the same thing. So once again, we'll put A to be this J of R prime, and the B is going to be minus grad of 1 over R minus R prime. And then we just replace and compute. And here, because we've already become experts at this thing, we can immediately drop all terms which represent any form of derivative with respect to the R coordinates on the R prime term. So anything that has a differential of A in this thing, I drop. Like this one here and this one, they're just 0 because A is J of R prime doesn't depend on R. I'm left with two terms, these two terms here. A with the divergence of B. A was just my J of R prime, and B was minus the grad. So here I have the divergence of grad, which is the Laplacian. Okay, and here that's the point at which we challenge your knowledge of these differential operators. There is an identity for the Laplacian of 1 over distance, which gives it in terms of the Dirac delta function. Right? So again, that's given to you tabulated in the notes. Essentially, the considerations that we had with Gauss's law at the very beginning are the equivalent of what we've got here. The discussions that we had with the potential, they're just giving you this relationship. Essentially, it's just Gauss's theorem manifesting itself in here. So this term is going to be non-zero. This term is just going to be 4 pi J of R prime with the delta function of R minus R prime. Fortunately, the other term, well, actually, it's giving us a little bit more work, but still we can just suffer through it once. So that's literally the second term that I have here, which is this fourth term here. So I have the J of R prime dotted into the gradient of, into the nabla of the gradient of 1 over R. So here we have to do a little bit more work. Again, the derivation is here. I'm just walking you through it. One of the things that you can do is rewrite the integral here in a more friendly manner by using a tiny trick. Here, what you operate this differential operator on is a function of R minus R prime. And there's nothing else. There are no other derivatives to be taken here. So as far as this term is concerned, you could elect to switch variables. And instead of taking a differential with respect to R, you take a differential with respect to the R prime at the cost of a minus sign, because the object here that you have is a function of a parameter, which is R minus R prime. So if you differentiate with respect to R, it's like differentiating with respect to the parameter. If you're differentiating with respect to R prime, it's like minus the differential with the parameter. So that's what this means. Okay. And with this trick, essentially, if you go back to the Biot-Savart equation, this is all under the integral sign. You can now rewrite the whole thing as the gradient of this big integral here with some r prime dependent things. And then this particular integral you can perform by doing partial integration in here. What you use as an identity is an identity for the divergence of a product of a scalar and a vector field, which is given here, that allows you to rewrite vector field dotted into nabla times scalar field. Actually, it's really just the divergence of the product of the two minus the differential acting on the other. Okay, so this is again an identity that's that you have in the notes for the divergence of this product of scalar and vector fields. Right? I'm sorry it's so boring. I'm sorry it's like so technical, but that's what it is. It's the price you pay for having chosen to study physics. That's what you're paid for. The nice thing about it is that it's non-negotiable. Okay. So what do we do with these terms now? Well, once we've done this partial integration trick in the first term here, we can now use just Gauss's theorem. Okay, I can transform the volume integral of the divergence of something into a surface integral of that thing evaluated on the surface. So that's the first term. And the second term, I can just leave unchanged as it is. So that's just directly rewritten as it is here. Okay, so then what do? We think a little bit about what these things are. This first term here represents an integral over an imaginary surface that encompasses the volume that I'm interested in here. If my surface, if my volume is kind of big enough, the current itself is going to start vanishing at some point. I can just choose my surface bigger than whatever region I have in which there's a non-zero current. Okay, and the integral still works, except that now at the boundary of that volume, the value of the current is just identically zero. Okay, so this particular contribution here is just zero. Okay, the only circumstance in which it would be non-zero is if I had a non-zero current density at infinity. But then you can say, haha, you are tricking us. Because, for example, if I do consider an infinite wire, then there is no length at which my j goes to zero. So you're cheating us, right? But then, yeah, fortunately, you can get away with it because you can just say that very, very far away, the current kind of comes back infinitely far away, and then you look still further than that, and it works. It looks fishy, but it works. So you can just put this integral to zero. The second integral here is, in the present circumstances, also understood to be zero. Because if we look at it carefully, what is contained in the integrand here is the divergence of j at the source point. And we have seen the continuity equation before, right? Div j plus d rho dt is equal to 0. And we are looking at steady configurations. That means that there is no change of the charge density anywhere. So d rho dt is 0. And therefore, div of j is 0. Okay, and that's a feature of these steady configurations that we are considering. So this one, in the present circumstances, is 0. We'll revisit it later. Okay, so this one's just gone. So in the end, with this monstrous calculation, the only non-zero term is actually the friendliest one that you have here, that you can just then substitute back into the original integral Biot-Savart. You've got the three-dimensional delta function here. So really, you can use that to resolve your integral. And what this means is that you obtain this form here. The curl of the magnetic field is given locally by just the current density. Okay, this is Ampere's law. Now, you have seen Ampere's law in the first course as well. However, I dare to think that you did not derive it like this from Jean-Sebastien. Perhaps you did. Right? Question.
Are there any exercises or circumstances in the text in which you should be able to derive it for moving to?
I would not ask you to derive that particular one. So this one is particularly long and painful. The thing that you benefit from by seeing this is how you manipulate such questions. Sometimes you need to compute the curl of something because you need it for a particular problem. Sometimes you need to compute the divergence of something, and that something might be an annoying product of things or whatever. And then in that particular circumstance, you would need to take steps which, at least in part, map one-to-one onto some of the steps that we have here. However, once again, the general cookbook of this is finite, very confined. You only care about the divs, you only care about the curve. Okay? Of course, the Laplacian is included in there automatically if you also say, yeah, but we have the gradient as well. All these things. Okay? So these are the operators you're dealing with. You don't need any more. If you apply these operators onto complicated products of functions, then of course there are going to be identities giving you how these products decompose into sums of differential operators here and there. These equations you don't need to know by heart, but you should be confident enough to say, bring it on. Whatever product you have, I don't care. 7 terms here, I will just do identity after identity after identity, and I will get there in the end, because there is nothing else but these identities products. You sometimes have to recognize some handy ones. For example, indeed, the Laplacian, this 1 over r being minus 4 pi the delta, that is something which would be given to you in a useful formula sheet. And this is one with a kind of pale green rectangle around it, meaning that you might forget the factor of 4 pi. It's okay, I'll give it to you, but you should definitely be able to use it in some circumstances. Okay, so you will rarely have to throw all the apparatus simultaneously in one go at everything here, like we've done here. But the individual bits, you should indeed feel like you've been there, done that. Yeah? Okay. Okay. Right. So so let's see. So that is the differential form of Ampere's law. And then just to finish this here, the one thing that we can do is invoke our good friend Stokes and his theorem to lift this to an integral form, which is really the kind of really useful one that that we can use in the next few minutes. So what do? We just take a certain surface and we integrate the curl of B on this surface, use Stokes' theorem to transform this to the line integral over the path defining this surface of dl dotted into B. And what that is simply the integral over the surface of this mu0 j. But then, of course, the picture that you have in mind is you have a certain surface and there's a volume current density piercing through it. So at each unit of time, there is a certain amount of charge going through. Okay, so you end up having something which corresponds to a current. Okay, going through this. So that's the integral form of Ampere's law. Okay, so let's just see how to use this in a couple of minutes. We go back to our simple problem that we had before. Okay, so I have my infinite wire like this, carrying a certain current I in that direction. And what am I going to do? I'm just going to use Ampere's law here in integral form. And I will first reason, because as per Gauss's theorem, here I can exploit Ampere's law in situations where I have symmetry. So I've got my wire, and my wire is infinite. So there's no dependence in the position I have along the wire. The field cannot depend on that coordinate along the wire. But also, what is up and what is down, it doesn't matter. I can rotate my viewpoint along the wire and nothing changes because the distribution of current hasn't changed. Okay? Therefore, the value of the magnetic field cannot depend on the angular variable around the wire. Okay? So the only possible dependence is with the distance to the wire. And if I think of my right-hand rule on this wire here, then my distance-dependent magnetic field can only be in the circumferential direction. Okay, so I need to have a field which is going to be coming out of the page like this here, at a certain value of a distance r here, with an intensity b that only depends on r here. Okay, so I'm not writing the vector here because, understand well, the intensity of the field is going to be the same, but as I move around the wire, the direction of the field also changes. Strength of the field doesn't. So what do? I want to invoke Ampere. I just say, and here we're going to help ourselves with this. We will define a wonderful Amperian loop like this that we will integrate along the wire. So here I'll just do from the top down, the kind of clockwise, counterclockwise integral of this. So what do I have? I have a loop which is at a fixed radius r on this, and I want to integrate on this path dl dot b. But I've said that b is only going to depend on the r, so the b itself is going to be a certain fixed intensity b of the distance. And now the direction, I've said that it was in the, so b is going to be b of r in the phi hat direction. Yeah, so phi hat is this direction, like this. So that's it. The dl is also in the phi hat direction. So the dot here just gets resolved. It's phi hat dot phi hat is equal to 1. And what do I get when I do the integral as I walk around here? I just get 2 pi r. And what must that be equal to? Well, Ampere tells me that this has to be mu0 times the enclosed current. But the enclosed current is just this current here, I. So that's it. You immediately get that your B has to be equal to mu0 I over 2 pi r in the phi hat direction. Okay? So it's really the one line derivation of what we have done before with this slightly stupid integral that we did. Okay? You've, again, I mean, in a sense, I hope I'm repeating stuff you've seen before, but maybe just like crystallize it a little bit more strongly, yeah? Because now you're more comfortable with where this Ampere's law comes from Biot-Savart. You have to be comfortable with where Biot-Savart comes from. But then I told you it was an experimental fact, so then you can say, okay, no more questions. Okay, so as per Gauss's law, Ampere's law allows you to compute the magnetic field in highly symmetric situations. If your situation is not highly symmetric, then you're screwed. Yeah, you can't really do it. But in these particular cases, then it's quite easy. Okay, there are other examples in the notes. So maybe see notes for there's one where it's a current sheet. So essentially what you have is a big, I'll just write the answers. You have a big current sheet in which there's a certain current going through here, and then the field ends up being, so the magnetic field ends up being like this here, and then here underneath. So that's one of the examples that please have a look at in the notes. Maybe the nice example to discuss very, very briefly is the example of a toroid, because it's got so many practical applications. So what does that mean? It means you take your favorite shape, okay, and then you've got your mold here, and what you do is you create a donut of that form. So now it's a full donut extension of that thing. So the cross section stays always the same, but the shape of the cross section is arbitrary, and it's completely rotationally invariant with respect to the central axis. So here, what happens in these circumstances is that, so if you circulate a certain current in this thing here, there's going to be a magnetic field created inside the toroid here. And then you can do exactly the same reasoning that we did before here, except that now you do an Ampérian loop where you integrate along one of the great circles of the thing here. And funny enough, the field has to have exactly also this dependence here, where now I is the current that goes through per unit length here. But again, the example is worked through in the notes. So this is quite magical, because irrespective of the shape of the cross section of your toroid, the magnetic field inside has only this like 1 over radial distance dependence. It's completely uniform except for this 1 over radius dependency. Okay, it's quite magical. It means that you can experimentally construct very, very controllable fields, even if you kind of mess up your machining for these things. Okay, but please have a look at these examples. They're relatively basic and simple applications of the integral form of Ampere's law. Okay,